Welcome to Insight Builder channel, exploring PyTorch on Raspberry Pi, hands-on tensor data manipulation for AI enthusiasts. We have been discussing regarding this particular topic for last 6 to 7 videos, and in this discussion we are going to work on layers like Flatten, Dropout, SoftMax. We will continue our discussion that where we discussed on the linear layer and using the embedding to pass through the linear layer. So all these things we have done. Let's move forward. In this discussion, we are going to create a new tensor with dimensions of these numbers and flatten it one by one. And then we are going to use something called as a sequential container to do the process as a flow. And then we will try to create a linear layer to accommodate the updated features of the tensor that we created. After we look at all this stuff, then we will see how to look at the dropout layer and the softmax layer. These are the points that we are going to cover. So let's begin. Let's import torch, and we will import from torch import nm. So these are the things that we are going to work with, and let us first of all create the tensor. The tensor that we are going to create is torch dot rand int. So this is the tensor that we are going to create, and the low value is 0, high value is 100, and the size that we are going to use is I comma 10 comma 15 comma 10 comma 10. So how will you read this many dimensions in a flow? So this is a 10 row 10 column matrix, right? But anything above this becomes batches. So this is a 15 batches of 10 row 10 column matrix, and then this is like 10 batches of 15 batches and 5 batches of 10 batches of 15 batches. So let me execute this, and this actually becomes a huge size. So if you take a look at the n element, there is a just a second. So in order to get the size of the tensor that has been created, you can use n element and you can actually multiply it by the item size. So once you do this, what will happen is you will actually get the, just a second. So you don't you don't need to use this. So it is actually 60 it is actually 600,000 bytes. So basically it is 600,000 divided by 1024. It's 585 KB. So, and if you further reduce it into 585 divided by 1024, it will be 0.5 MB. So if I do 585 divided by 586, then it will be almost 0.5 MB. So we have created a particular element, torch tensor, that is having a size of this much amount. But now just think about it. If we change the entire torch tensor, and this is actually a random integer. So in place of random integer, if I try to create a rand, and in case of rand, I don't need to provide all the the low and high value. And if I try to create a rand, it will be a float value. So if you look at it, it will take a second to even populate. And if you run the same value, you will see it is much lower. So this is having almost 300,000, which is half the size of the integer, right? So, and if you look at the type, if you look at the type, okay. So this is actually a float tensor, and you can actually modify the float tensor. You can increase the size of the number of decimal places it can have, and all those stuff you can do. So like this, you can actually get the size that each of the element that you create uses on your RAM. The reason why I'm sharing these things is that you should be able to visualize what these numbers are actually doing on your RAM and how much space it is occupying, because these numbers are very huge. the item size alone, if you look at the item size, there are almost 75,000 items in that random tensor that we have created right now. So that is excuse me, this item size and the n element, sorry, n element, we are going to have 75,000. So this is something that you guys have to understand how these things are coming. Once you know that there are 75,000 elements, as we apply flatten, then the final flatten value should be 75,000 elements. So let's proceed. Let's go to T, and we are going to create a flatten one model, FL1, and here I'm going to say NN flatten. And in the flatten, you can actually give two dimensions. You can give the start dimension and the end dimension. The start dimension is the dimension from which, just a minute, it is the dimension from which you want the flattening to happen. So I have taken this much long number of, higher dimension tensor, so that I can show you what happens as we apply the flatten on each of the dimension, so that you will see how the things are changing. Okay, now what I'm going to do is, first of all, I'm going to apply the start dimension, this start dimension on this particular dimension. This particular dimension, that is 0, 1, 2, and 4. 0, 1, 2, 3, and 4. So this will be the third one, 0, 1, 2, 3. And the start dimension is 3. And the end dimension by default it is -1, right? And anyway, you can provide that and execute this. So this will only create the model, but now you have to apply this particular layer on top of the element tensor T, right? So let us do this, FL1 on T, and once you execute it, you will see that the same kind of matrices come up, but once you look at the size, you will see the difference. Excuse me. So you'll see now it is applied on the last two elements of the size, and the last two elements have been multiplied together and it has become 100. Next, what we are going to do is we are going to continue this process, and instead of third dimension, I'm going to do it on the second dimension, just to move up and to show you how the dimension looks. So now it will be applied on 15. So what will happen is 15, 10, 10, all these three will be multiplied together and we will get 1500. So 5, 10, 1500 we will get. So let us execute this and let us do the size value. So I have done the flatten on T size, and you will see it is 1500. Next, what you are going to do is we are going to do it on first dimension. That is, we are going to do it on the dimension that you see here. So it will be done on 10, right? So we are going to do that and execute it. Here you see that it has become 5, 15,000. And finally, if you do it on dimension 0, you will see that it becomes total 75,000. So it becomes a single 75,000 element tensor. And if you look at the tensor output right now, it will be just like sorry about that. It has to be assigned to something. So let me say temp, and let me remove this. Execute it. Temp. If you look at the temp right now, it will be a linear single dimension tensor. So it is as simple as that. Now what we are going to do is, you have seen how the flatten works, but let us take one real world scenario. Real world scenarios, you will be having such kind of higher batches of sensor or higher dimension of tensors when you are working with the pictures, right? So let us for a moment assume that you have a tensor. Let it be T again, and we are going to say torch rand int. We will take rand, and we are going to request for 15 pictures of 28 cross 28 pixels. Basically the picture will be of width 28 pixels and depth 28 pixels, and there are 15 pictures like that. So once you create such a picture, once you download such a picture into the Python execution environment, it will be like this. It will be full of pixels, and it will be of size that you see here. So it will be of size 15, 28, 28. However, when you are going to use these pixels as features into your neural networks, you have to convert this into a single dimension. So in order to convert this into a single dimension, you can create fl2 flatten2, and you can call nn.flatten, and we can say that start dimension is 1. So once you say that start dimension is 1, and if you say t2, so I'm just creating a new tensor, and I'm going to run flatten 2, that is the flatten layer that I have created here, on this particular tensor that I created just now. That is the 15 bytes of 28 cross 28 pictures. Once you do that, once you look at the t2, you'll see that it has become now there will be 15 rows of 784 elements. So let us look at the size. Let us look at the size, and you will see 15 rows of 784 pixels. So that is how the things change, right? So this is the main point I wanted to talk to you about, because once you have such a output, then you can start building the neural network layer. So let us actually create a lin picture, because we are going to work on the pictures, and we have a linear model that we are going to create. So we are going to say linear, and in the linear, the features that we are going to use, the in features are going to be 784, right? So we just now have seen this value 784, and the out features we want to have it as 3. We will have it as 3, and let's execute this. Next, for we in the last video we saw how to look at the parameters of the linear model. We will be doing that right now. So lin pic. The reason why I'm going through this again and again is that you guys have to go through this and get familiarized with how the internal parameters look, so that you can visualize what is going on. Most of the time we forget, or we don't realize how the internals are, and it becomes really tedious to do programming. So now here you see that there is three rows here, and this row will be 784 in number. The elements in this row will be 784 in number, and you will have 3 biases also. So basically what happens is the linear model that has been created actually creates like it assumes that it is going to be a it is going to be an equation that is having 784 variables. So all these are variables, and these are called as weights. So weight, this is the weight parameter, and this is the bias parameter. So you can see that here also. So that is the point I wanted you guys to visualize and look at it. Next, what you are going to do is, if I am going to take the tensor that we have here, okay, and if you are going to apply the tensor on this in this linear layer, then you will get an output of 3 parameters output, 3 column output. So let us apply that. So let us say lin output and linear output basically. So I'm going to say lin pic, and I'm going to call the t2 tensor, and I'm going to execute this. So once I do that, all the 15 rows of the t2 tensor would have passed through, and if I look at the lin output, you will see that we have got three different columns of 15 rows. So by now we have actually gone through the entire process of the practice that I was talking about, and all this practice you don't need actually any of the pictures. The reason why I'm not using any real life picture is that it becomes a bit of a confusion to think that okay, picture has been converted to the matrices or elements, and then we are working on it. So there is some kind of a lag that happens in my understanding at least. So I felt that okay, let us do it only through numbers, and through something that we don't actually import, or we don't load it through any other library. So to avoid all those confusion, I had just used the numbers. So we have done till here. All the steps we have done, the 4 steps. Next, we are going to look at the dropout layer as well as the softmax layer. So the purpose of the dropout layer is that it drops out couple of elements and makes them zero as we pass through that layer. This is helpful when you are going to make the neural networks to learn. So I'll be showing you the example. So we have the lin output, right? I just want to execute it and show you the output again. So this is the output. I'm going to create a DO layer, that is dropout layer, DOL, and NN called dropout. And in the dropout, I am going to say the probability is 0.7, right? Dropout, we are going to say the dropout probability is 0.7, and I am going to send this lin output into this dropout. So what happens is, you'll see that a couple of elements or a couple of numbers on this tensor matrix will become zero. So let's do that, and I'm not assigning that to anything. So just a second. Lin output, and now you'll see that most of the things are becoming zero because I have taken a dropout of 0.7. Now assume that I do something different. So I take 0.3 as the dropout, and I again send it through this. You will see most of the numbers are still present, but couple of numbers have become zero. So that is 30% of probability wise the dropout happens. So when you are going to run this entire model into various layers inside the model, the model can start learning better. So that is the idea of the dropout. There is an option to use in place in dropout, but you don't need to prefer that. So you can use in place. By default it is false, so you don't need to make it true. If you make it true, then what will happen is it will directly change the tensor value itself once you apply to it. So that may not be required when you are going to apply it in a model level. That is a dropout layer. The next thing is called as SoftMax. SoftMax is like, it is better to show you what happens. So let me SoftMax. So you do SoftMax, you call this. By default the dimension will be 1. You can say by default the dimension will be none, and you can actually give the dimension on which you want to do the SoftMax. So usually the dimension 1 is preferred because we want to do it on the column level, right? So you can do it on the dimension 1, or it will do, or else what it will happen is that basically what happens is, whenever you are going to apply this softmax, it actually looks at the numbers and it converts those numbers to a range between 0 and 1, and once you add it, it will become 1. So that is the idea. So let us execute this, and then let us execute the output. Let us execute the output, and we executed the value on the output. So you'll see that if you add these 3 elements, so let me take these 3 elements, I'm copying it, I'm putting it here, and I'm going to add it right now using plus. One benefit of being in console, and you'll see it adds up to 1, right? So that is how the softmax works, and it doesn't stop at softmax. So assume that this is an output that is coming from the classification problem. So in the classification problem, we will want to know which class is being selected as max. So for that, there is something called as Argmax. So if I take this output and place it on temp variable, I execute it, and if I ask for the Argmax, and if I execute it, just a minute. So if I execute it on temp Argmax with dimension of 1, that is on the columns again, then it will actually choose the column that is having the maximum value, and that value will be sent back. So you see that it has sent back 15 numbers, 15 indices of each row in which the maximum number is present. So you can take a look at it on 5th row. So if you go to the 5th row, 1, 2, 3, 4, 5. So out of these 3 numbers, this number is the max value, and like this number is the max value. 0. Most of the time 0 is the max value, and that is the output that you get. And once you get this output, you can compare it with the class value that you already have. So right now in this particular discussion, in this brief introduction, we saw how we can actually work with Flatten, and how important it is. Also, this is one of the exercise that you can club it with the earlier video, and you can complete it in a single go whenever you are learning Torch or PyTorch. So once you become more fluent and comfortable with this step, until introducing softmax layer and dropout layer, after you are comfortable, then we can go to understanding how the loss functions work, and how the backward propagation can be initiated on the loss function. So those becomes way more comfortable and easier once you are once you look at these data and become more conversant. So we saw how the flatten works, and then we introduced just to bring a linear layer and started doing the forward pass, and then we went ahead and introduced dropout layer, and then finally we also saw the softmax layer. In the next video, we'll continue this discussion and introduce the loss functions, and how we are going to move forward on creating and training the models. With that said, I would like to leave this video with 4 words, that is practice, 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 practice. See you guys. Have a great time.